Thanks, everyone. Harold unfortunately broke his collarbone, so he's not able to give this presentation, but he really wanted to be here, so I'm here in his place. I'm Justin. I lead the team at Netflix that decides what recommendations to show on the homepage. So to get started, there's a really basic idea behind this paper, which is that if a user has a certain distribution over interest, say in this simple example, if someone's watched 70 romance movies and 30 action movies, you'd expect that the recommendations you might want to serve to that person would also be calibrated. So 70% of the recommendations should be romance and 30% should be action. And you would want to do this so that you can accurately match the interests of the user and treat them all fairly with the right proportions. So what's the problem with this? Well, typically we don't actually optimize recommendation algorithms against this type of metric, and instead we optimize for accuracy. And optimizing for accuracy often leads to having uncalibrated recommendations. And in particular, when you optimize for accuracy, they can especially amplify the majority interests of the user, then that will end up crowding out the minority interests of the user. And I'll show two kind of simplified examples of this to show why this happens. So in the most basic case, you can think of just having a binary classification problem where you have no features. And again, you have this user where you've observed this distribution of interests in the past. And if you know nothing about the items you're recommending, to maximize your accuracy, you would end up just recommending all romance movies. So you get about an accuracy of 70% in that case. If instead you said, well, you could do, what if you just did some kind of sampling instead in this problem and you tried to match the interest distribution, you'd actually have a lower accuracy by doing the sampling. So this isn't just a property of like a really reductive situation like this binary classification. You can also find this happening when you have a model like LDA. So with LDA, you have a generative model where you start off kind of with the right, you have understanding the user's interest proportions for a topic, which we're going to refer to as a genre. And then from that genre, you sample a word, or in our case, a video, from that topic. And so when you do the sampling procedure, you'd expect that you would be able to preserve these genre distributions. But what typically happens is that, like in the binary classification case, you don't end up wanting to do the sampling because that doesn't give you as good accuracy as if instead you're going to rank the recommendations from an LDA model using the actual probability for each item given the user by marginalizing over all of the all the genres in the user's interest. And so this gives you increased accuracy, but then in doing so, you don't have the calibrated genre proportions anymore. So this type of problem can happen with a lot of different types of models, even ones that have this latent factors or try to model these distributions inside. So how do we measure when a model is producing calibrated recommendations or not? So to start with, we can have the building block, which is the distribution of genres for a given movie, which is shown here in the first term. And then this doesn't have to be binary, so it can have different probabilities for different elements of each genre or other type of categorization you have. Then we can simply aggregate those for each of the movies that a user has watched using their play history, potentially with a weight on each one to have some decay across time to give more representation to different ones. And then to handle cold start problems and diversity, you can also add a prior term where you have some base distribution of genres that you also add into the user's distribution. Then we can use that. Then we can similarly also define the genre distribution over a list of items, which is here represented by Q. And in this case, what we do is we again take the distribution of each item, weight it by some rank, so that you might give higher weight to the items higher on the list, and lower weight to the items lower on their list, and then get the distribution for that list. So what's a metric that we could use with these building blocks to look at the difference between the distribution for the user and the distribution of a list of recommendations? One obvious one is the KL divergence for this, which is defined here. So we can combine the user probabilities with the list probabilities, and we have to be careful just to make sure we don't have places where there's no support in the list distribution by adding a smoothing term to the bottom part. This type of approach, the paper focuses on the Cal divergence, but you can use other F divergences like the Hellinger distance as well. So given this metric, how can we then actually use this to build more calibrated recommendations? So because calibration is a list-based property and recommendation systems are usually trained with either point-wise or pairwise objective, the easiest way to address this calibration is by putting it into the post-processing step of your recommendation system. So you've already run some your base recommender, you get some scores predicted by that system. And then what you want to do is build then a re-ranked list of items that maximizes a trade-off between the score predicted by the recommender plus the calibration that you want to provide here. And in this case, we subtract off the calibration because a smaller calibration is actually a better score. Also, one nice thing about breaking it down this way is if you have different categories, so you might have something like genres, but maybe you also want to maintain TV movie balance or something around country of origin balance, you can add those as individual terms and have different parameters trading off the different methods. So if we take the Cal divergence and plug this in here, we can run a greedy algorithm. But if you go through and actually look at simplifying the optimization problem, what you see here is that the resulting function is actually submodular. So going through and optimizing this with a greedy algorithm provides the nice optimality guarantees that you get with a submodular function. And those optimality guarantees are also provided for each sublist up to length n. This work is related to kind of two different concepts that have been done in the field. So one is it's related to some concepts of fairness from machine learning. In this case, it's focusing on the calibration notion of fairness for the user as contrasted to other types of fairness. This is also similar to work that's done in diversity in recommendations, but it's different in that we're not defining the diversity with respect to some similarity measure across items, but instead trying to match the distribution of taste for the user. So an example would be if in the previous case, if you had the person who's watching romance and action, if you put in a kid's recommendation, that might really do well in a diversity score, but would really not be matching the distributions of interest of the user. Into the experiments on this. So these experiments were done on the Movie Lens 20 million data set. Here, what it's looking at is doing re-ranking off of a baseline model, which is weighted matrix factorization. The plot here, what we see is we can start with just looking at the red curve, which is just having just the output of the recommendation system. And you can see with the calibration metric that a lower score is better. So the initial calibration is not very good. There's a pretty wide distribution in terms of the calibration scores. But then as you increase the weight on the calibration factor, you're able to get the recommendations more and more calibrated to the interests of the user. So it seems like we can put that in and have and increase the calibration. So what do we trade off in terms of the accuracy? So you can hear looking at the recall at 10 and 50 compared to the calibration at 10 and 50 with the Cal divergence. You can see that we're able to actually greatly increase the calibration while with a pretty small decrease in recall, especially let's say at 50 in the list, up until you set it to very high parameters. So you're able to improve the calibration quite a bit without degrading the recommendation accuracy. This is an example of a user who in the initial recommendations would have a very uncalibrated set. So the middle bar is the distribution from their play history. The bar on the left is the before calibration, and the bar on the right is the after calibration across all these different genres. The circled items is showing that these kind of smaller genres for the user without calibration, the recommendations actually get nothing in the set. But then with the calibration, and then a lot of the majority interests are overrepresented, and then the calibration will bring up the smaller interests to be closer to what is actually in the user history. To show this isn't just one single user that it works for, these are the users that have the lowest calibration initially over the whole data set of the lowest 10%. And you can see that the A lot of these genres are underrepresented initially for these different users, and then with the calibration, it's able to bring them much closer to the actual distributions that you see in the data set. So to conclude, unbalanced recommendations is a pretty typical result if you're training your recommendation models for accuracy, especially when you're dealing with limited amounts of data for each user. And calibration is able to provide fairness and proportionality with respect to the interests of the user. And it's able to do this by using a submodular function in the post-processing step that provides a nice efficient optimization plus an optimality guarantee, so you can easily plug it into as a post-processing step on a lot of recommendations. Thank you.
Thank you very much.
Hi.
Hey, Sophia from Outbrain. So have you used this approach for live A/B testing, and if so, what did you get there?
So I can't comment on the A/B testing results that we have. I think the question might be, where would you want to use a technique like this, across different recommendation systems? And I think, it's in those cases where, you're not just trying to target accuracy, and you're trying to think about, how are you going to have, you're showing a whole list, and you want to balance having some elements of diversity and making sure people will see a good representation of their full set of interests in it.
Okay, so in terms of KPIs, this is not something that it's not the main goal of this, basically.
I can't talk about the A/B test results with regards to this.
Oh, okay, thank you.
Hi, thank you for a great talk. I'm Rama from NIT India. So most of the movies cannot be classified into a single genre. So how does calibration work in those kind of scenarios?
Yeah, so the base assumption isn't, you don't have to have a single genre classification for each item. So as long as you have for each item some probability distribution over some set of categories, you can think of them as genres, but they can be whatever type of category you want. You can have these soft assignments, and as long as the weight of each one for each item sums to 1, you can apply this method to it.
Hi, I'm Abik from Disney. I was just wondering, the recalibration approach at the end that you use, how much time does it add to the, producing the final results?
I think it depends, of course, on the number of items you have and the how many genres you're looking at and so on. But it's a very efficient method. You're just kind of for each item in the each position in the list, you're just doing it's a number of items times a number of genres type of operation. So it's pretty fast compared to a lot of other types of computations you might need to do in your system.
Okay, thank you.
Hi, I'm Arnie from Flipboard. So I have a question about so when you're saying that a user watched 70% action movies and 30% let's say sports movies, isn't part of that also because there are a lot fewer sports movies, and is it the right thing to calibrate to that? Because you might end up boosting a lot of things that just aren't that there aren't that many in the data set to begin with.
I mean, I think. So you're saying if you don't have good support, there aren't very good items to recommend from that part of the distribution, maybe you don't want to do that. I mean, I think the idea is, hopefully if that was the case, that would show up in your accuracy, the scores that come out of the recommendation model, so that if you set the trade-off parameter pretty well across your population, hopefully you wouldn't have those actually bubble up too high in the recommendation.
Just a follow-up to that, actually. So because you mentioned about some genre distribution, can you encode some of that IDF weighting or something like that into the model, so that your calibrations actually take into account how whether the genres are actually popular or not? Because I'm guessing the genre also has a long tail distribution.
So I would hope that if you have those are the type of things that the accuracy model would deal with, and so this is more about saying, for that user, what is their interest, and trying to be fair to those, and trying to say, I want to ignore the those other signals that a traditional recommender would try to actually optimize for and use.
Cool, thank you.
Hi, this is Surendra from Flipkart India. I have a question. So you're talking about accuracy and then the need for calibration. If I draw parallel with explore-exploit phenomenon, you're trying to get away from exploit-only mechanism. So did you also baseline against some methods, probability matching techniques like, say, Thompson sampling or other explore-exploit methods?
I think explore exploit would be a little orthogonal to this. If you can see, this is there's a version of it where you put in a prior that would hopefully induce some exploration over the set of items that you have, but it's really saying you can think of it as more of an exploit type model because you're saying I have a lot of data about this user and I want to make sure that the recommendations match the calibration. You could layer in some kind of explore exploit again into the recommender that this is built on top of, but you need to make sure you understand how those two systems would interact.
Okay.
Hi, I'm Gordon from Asos. Thank you for a great paper. So
it's not my paper, but
pass my pencil. So one of the key parts is the weights for the user history. You're actually trying to that defines your calibration. You're trying to match that, the distribution. So how do you decide what is a good set of weights? I imagine that's a big rabbit hole you could go down in terms of, I don't know, whatever.
Yeah, in the paper, they're just uniform. I think that's just the typical thing for your domain. You might want to figure out, how to put in some kind of decay function if that's based on time or sequence or something. You can play with those and tune them. But I think, typically those are the types of things you might have to tune, downstream of a system like this.
Thank you.
Hi, I'm here.
Yeah.
I'm Paolo from Polimi.
Yeah.
When you use the score from the recommended system, do you mean the rating, the estimated rating, I assume? And if this is the case, how do you manage the score produced by ranking, learning to rank algorithms? Because with learning to rank algorithms, the score has no, let's say, upper bound somehow. So there is no physical meaning with the score.
Yeah, I think this is abstracted from exactly what the score is. So I think in this case, he was doing kind of a typical implicit feedback, learning to rank inspired system. So as long as you have some score and it's reasonable, it's not going to be like totally swinging all over the place for different users. I think you could do it. If not, you can apply like some kind of calibration technique to the score itself, so at least the score distributions are calibrated so that you get a good range, so you can be confident about the range that you're going to be able to plug that into for the next, for doing the post-processing step.
Thanks.
Hi, this is Shenxing from Uber. So my question kind of related to the A/B test, but not asking you like a result from A/B test. So my first question, a quick question is, have you already productionalized this model in the Netflix system? Or is it just also still at a research stage?
So I can't comment on exactly what we've productionized or not in the system. But we're always trying new things and testing with A/B tests. And so obviously this is an interesting idea. So
yeah. My second question is it's a very interesting idea. But so if you have a plan to productionize this idea, do you need to come up with new KPIs, or this work is already aligned with a company or business KPIs already?
Yeah, I mean, I think things like diversity or calibration, they align with the types of metrics we look at because we typically want to optimize for long-term user engagement. So when we run A/B tests, we typically look at retention because we're a subscription company, which means retention is something you measure over at least a month, if not multiple months, and then looking at things that are correlated with that, like how much how engaged with people are, how much they stream, how often they visit the site, and to do those things, if you just optimize only for accuracy, you're probably not going to do a good job.
I see. So you have some data to say, okay, this is correlated with user retention.
So when we A/B test, typically, we look at retention and things that are correlated with it.
Cool, thanks.
Okay, we have two more quick questions, please.
Hi, I'm Reza from Zalando. I'm here.
Okay. Yeah, there you go. Okay.
Yeah, quick question. So on an unbalanced data, training for accuracy is bound to fail anyways. And here we do the calibration. I wonder what is your take on training not for accuracy, but for better metrics and including multitasks like diversity and others from the beginning instead of fixing something that is broken?
Yeah, so I think that's something you could potentially think of as future work, of how you would layer this into the training objectives themselves. But I think ultimately, just doing, it's always a balance between the two sides, but I don't think there's an existing solution for that.
Thanks.
Hi, thanks for the very interesting work. I'm Monchan from Senegal. So, do you think your method can work well for like more categories, and scale to like a large amount of categories?
It's like, how does it scale with the number of categories? Is that your question?
The performance and the scalability.
Yeah, I think it depends a lot on like the density of the category. So, if you have a sparse distribution, you could probably scale it pretty well. But if it's if you have a very dense, set of categories where there's some small probability of each one, then it scales with the number of categories times the number of items times the number of things in the list. So you would want to make sure that that doesn't get too big.
Very last one.
Maple. My understanding is the calibration is not personalized to users. It's global, right? Across the model. How much you calibrate for?
Yeah. In this one, the calibration weight is global.
Yeah. So do you think there is value or opportunity to personalize it, or do you feel like, do you have any intuition whether there is room for personalizing here, or maybe it's something typically fixed for a large group of users?
I think you could potentially look at, if people tend to be constantly watching things that are, very different from what they're already doing. But I think if you think about having the prior in there, I think it would mostly just be for users who are very low activity. And so it could be something you might want to do, but I'd have to think through how you'd actually make that work.
Thank you.
Yeah, thank you very much
Thanks.
again.